During the early years of the Cold War, the United States Air Force's Strategic Air Command had a straightforward defense doctrine. If the confrontation heated up, they would have fighter and nuclear bomber planes that were too swift to catch. It was hoped that this unique aircraft would be able to sprint into the Soviet Union and Chinese territory at speeds and altitudes that enemy missiles would be unable to achieve. To accomplish this, they required an extremely fast jet with a daring design capable of putting on a spectacular display. Convair responded to their needs by delivering the world's first operational supersonic bomber, the B-58 Hustler. The Hustler served as the model plane for a new era of amazing aircraft. The B-58, with its dazzling eye-catching armor, sleek delta-wing design, roaring takeoff, and infamous sonic boom, was regarded as a great projection of American power and strength. B-58s established numerous world records, some of which still exist today. However, 22% of the built Hustlers were destroyed in terrible situations. Even the most expert pilots were scared of flying it, and the Soviet Air Force's combat future was jeopardized before it ever began. In the Hustler's instance, anti-aircraft technology advanced quickly than supersonic flight. On Monday afternoon, October 29, 1956, the delta-wing supersonic B-58 moved for the first time under its power. This occurred during a preliminary taxi maneuver designed to test the B-58's braking turning radius and overall ground handling characteristics. To this point, the aircraft had undergone an Air Force Safety Board inspection, ground vibration checks, engine runs to full military power, and a variety of additional checks, all of which demonstrated it was ready for the taxi test phase of operations. The conveyor flight crew for this No. 1 B-58 is pilot Ericsson flight observer Mach and observer Harrison. Ericsson, who flew the first B-36 and YB-60, is the flying department manager for Convair's Fort Worth branch. At around 16:30 hours, the B-58 with the flight crew aboard was pushed out of engine run station number 2 and hauled to the starting position for the initial taxi maneuver. During this test, taxi screens were fitted to the jets to prevent damage from foreign objects. This test began near the north end of the runway on the east-west taxi strip. The plane was joined by ground support equipment and fire trucks. Canopies were closed at around 1700 hours. Engines were started, and as darkness fell, the B-58 moved onto the runway and performed its first taxi maneuver. This test demonstrated the B-58's good ground handling qualities, and the aircraft was cleared for taxi runs. 1 week later, on November 5, 1956, the B-58 moved out of engine run station number 2 under its power and completed its second taxi run. This was a low-speed run from north to south at around 40 knots. Excessive braking temperature developed in the aft inboard duals of the left main gear during the return taxi, causing a tire to blow after the plane had come to a halt on the taxiway. As soon as the wheel cooled, ground crews arrived to remove the tire and investigate the reason for the failure. An examination indicated that the high temperature in the wheel was caused by a brake that did not fully release. The tire repair took around 20 minutes, and the airplane was taken to the development hangar building to correct the brake system difference. The first high-speed taxi was created on Wednesday morning, November 7, 1956. This run was completed at a maximum speed of about 92 knots. For a brief period of time, the airplane's nose was lifted into takeoff position. Then the power was turned off, and the drag chute was deployed. There were no noteworthy inconsistencies observed throughout this run. The second high-speed taxi was built after nightfall on November 8, 1956. During this 138-knot run, the aircraft's full weight was lifted from the landing gear. On November 10, 1956, the B-58 flew its third high-speed taxi. This voyage was performed from north to south with a top speed of 148 knots. The only issue found was a tiny leak in the hydraulic system of the power control linkage package. On Sunday afternoon, November 11, 1956, when America was celebrating Veterans Day, the B-58 taxied to the takeoff position for its first flight. ground testing was now completed. The specifications had been met, and the B-58 was prepared for its first flight. The weather for this occasion was ideal. The skies were clear, the air was moderate, and there was a light breeze from the south. The chase aircraft for this mission were a Convair YF-102A for observation and an F-94C for aerial cameras. At 14:39 hours, the chase planes dropped their brakes, engaged their afterburners, and launched to the skies. After waiting just long enough for the chase planes to move, and the B-58 released its brakes and began its takeoff roll. The afterburners were not used. The B-58 took off at 14:41 hours following a 3,300-foot ground roll. The airspeed upon takeoff was 160 knots. The takeoff was regular and the rise was consistent. The Flight Test Department received special flight data from the B-58 via telemetered transmission to a ground recording device. This data was tracked throughout the journey and saved for future analysis. The information gathered here is augmented by additional flying data captured on the aircraft. Future flights will be covered similarly. After takeoff, the B-58, with landing gear extended, soared to 10,000 feet. The high landing gear allows the long fuselage to produce the requisite ground angle for takeoff and landing. The gear was withdrawn when the plane was still at 10,000 feet. The operation went quickly and smoothly. Climbing to 20,000 feet, the airplane was flown at 0.7 Mach. At 15:19 hours, exactly 38 minutes after takeoff, the B-58 landed on the runway and completed its first flight. The drag chute was deployed promptly upon touchdown, and the plane came to a quick stop with minimal braking. The B-58 had completed its first flight with ease. The performance of the engines and the airplane had been normal. At around 15:24 hours, the B-58 Supersonic bomber nosed into the engine run station, marking the end of its first aerial trip. The mechanical reactions of this airplane to its first flight are caught on tape. The crew's faces, however, will reveal the human element's reaction to the B-58. Of course, this is just the beginning. The B-58 will undergo numerous hours of arduous flight tests before it can be adequately evaluated as a weapon for the United States Air Force. However, based on the initial flight, it is realistic to expect the Convair Supersonic B-58 to usher in a new era of American aviation dominance. The B-58 weapon system has seen its share of remarkable days. Days when its performance surpassed the historical standards of manned flight. September 18, 1959, Carswell Air Force Base, Texas. On this date, the B-58 demonstrated its low-level assault capability, resulting in an unprecedented flight feat. In its race across 4 states from Texas to California, the Hustler flew at speeds near the speed of sound and never rose more than 500 feet above the ground. What was the flight's strategic value? First, it confirmed the hypothesis that high-speed, low-level hits are possible without sacrifice in B-58 high-altitude supersonic operations. Just 1 week later, this same aircraft demonstrated its high-altitude capacity by flying from Seattle to Waco at an average speed of 20 miles per minute. Next, the on-the-deck flight to California made the adversary open to another kind of assault. By skirting valleys and skimming mountaintops, the B-58 can glide beneath enemy radar nets and bypass missile positions, making line-of-sight retaliation nearly impossible. Unique, low-level, high-speed capacity penetration with minimum risk, crushing hitting power, and the best chance of survival. This is the total of what the B-58 did in a few hours on September 18, 1959.
One thing about the B-58, we would take off not fully loaded. The airplane, when it was with no fuel, only weighed about 55,000 pounds, and the total thrust was about 60,000 pounds. When we took off, we went and refueled, and we brought on a lot more fuel than we could have had on board when we took off. Typical mission, we'd fly a high-altitude navigation leg, do some high-altitude bomb runs. I can't say bomb drops because we never dropped bombs. We were scored by these Nike radar sites. They would electronically score where a bomb would have hit. We always had to get within 2,000 feet of the target. Low altitude bomb runs, I think that's where we excelled compared to the B-47 and the B-52. We went in low level, and it would be about maybe 30 to 40 minutes of low altitude navigation right on the deck and just below the speed of sound, about 0.91 Mach number. And as we came in and ran these bomb runs on these Nike sites, very often they could not pick us up. They could not tell us where we were looking at the ground clutter because we were, pretty much right on treetop level. So quite often those Nike operators would ask us to pop up so they could acquire us on radar. And, we would do that, then go back down on the ground and come on in. That was a low level mission. And B-52s, B-47s pretty much did the same thing. They tried to emulate the wartime mission as much as possible. The thing I liked about the B-58, because the navigation and bombing system was so accurate, I flew a lot of times in what was called radar silent. I would actually put the radar on standby so it wasn't emitting any radiation at all. And I would have a dial that I could look at and see where the crosshairs would be if they were supposed to be on a checkpoint where I could update my latitude and longitude. And when I came close enough, I would turn the radar to on from standby. And sure enough, those crosshairs would be sitting pretty close to where that radar checkpoint would be. So it was just a slight adjustment, if there was any adjustment at all, and then I would turn the radar back off. We had Doppler radar in the back of the aircraft, but the Doppler radar gave us ground speed and wind drift. But the Doppler radar was a very pencil thin radiation straight below the aircraft, so that really couldn't be picked up by enemy radars.
De November 1960. Holloman Test Range, New Mexico. What's the mission to launch a fully automated weapon at Mach 2, twice the speed of sound, from 50,000 feet? A B-58 Hustler completed the mission today, capping a series of test drops. The pod separated cleanly. The free-fall bomb dropped along a predetermined course. For the crew, everything was usual. However, one of the flights provided Colonel James Johnson, commander of the 1st B-58 Wing Grounds, to believe that we should get the finest targets because we have the best airplane. While the official report might read as usual, the reality inside the cockpit during these high-stakes, high-speed missions was a tense dance of precision technology and human reaction.
Oh, let's see. I remember one of the first times I went supersonic Mach 2 simulated bomb run in the B-58. We were coming in from the northwest to St. Louis Nike site, and on those you pick a target and report it on the radio what your target is, and the ground radar tracks your position, and you tell them which target you're going against, and when you reach the bomb release point, you don't actually release a bomb, but a tone breaks on that radio frequency, and the computer picks up its stylus and figures out where the bomb would have hit had we really released one. Well, we're up there at 50,000 feet coming in at Mach 2. We had 100-knot tailwind, so we're doing over 1,300 miles an hour ground speed. And just leveled off and 50,000 feet and everything's looking good, so I engaged the autopilot. Yeah, okay, that looks pretty good. And I engaged the auto throttles. I'm just relaxing a little bit. Everything's looking good. And whoop, 60 degrees of bank to the right. What's going on here? Whoop, 60 degrees of bank to the left. holy smokes, and I kicked off the autopilot, and I'm flying it manually now on the stick, and I says, what the heck happened, Herc? My navigator. He says, well, the crosshairs moved off the target to the right, so I moved him back to the left. I says, well, you sack of something, you should let me know when you're doing that, because, so here I am at 60 degrees of bank trying to center up the bomb aiming device. 20 seconds to go, we turn on the tone on radio frequency, and I'm still centering the aiming point. And just as the tone breaks, I'm rolling wings level on with it level. And I thought, okay, score that one, bomb plot. And you got to, what happens, even though it's just a simulated bomb run, you have to be scored so close to the target that it would be an effective release. If not, you have to go to what we call the bloodbath the next day. That was a bad bomb board, and determine whether it was crew error or equipment, what was the problem. So we're a little concerned, and I bring the throttles out of afterburner. We're descending down to subsonic altitude, about 30,000 feet, hanging forward in the harness, because even though we're still at 100% with the afterburners off, we're decelerating so fast that you're thrown forward in the harness. We get down to 30,000 feet, and we're given our post-release information, our true airspeed and the wind and heading and stuff, so they can score it. And we're waiting and waiting and waiting for the score, hoping we don't have to go to the bloodbath the next day. And the score finally comes back as a Type 2C abort. I said, what's that? I have no idea. So the navigator gets out his book and thumbs through it to find out what the heck is it, and he finds that what it is says that the aircraft maneuvers exceeded the capability of the computer to figure out where it would have dropped, where it would have hit. And the small print says that if the crosshairs were on the aiming point, you get credit for a good release. So, hooray, we knew we were okay.
September 13th, 14th. Stierk Bergstrom Air Force Base, Texas. The 13th marked the start of the 1960 SAC combat competition. On its debut, the B-58 Hustler won the High and Low-Level Bombing Award for its 43rd Bomb Wing crew, making it the first bomber to get such an award so soon after entering SAC's inventory. With barely 40 days of preparation, a lone B-58 and 2 air crews faced up against 24 other crack crews flying 12 other bombers with thousands of operating hours under their wings. The B-58 crew demonstrated the quick reaction capability of SAC's new weapon system. They approached the plane boarded, started the engines, and got the wheels rolling in 2 minutes and 10 seconds, which was half the time taken by SAC's other operating bombers. And crews received 200 out of a possible 200 points for this event. Using only one combat-ready B-58 for both missions, its 2 crews collected 1,046 points, 137, behind the first-place finisher. The accuracy of both radar bombing flights exceeded the aircraft's specification standards. And aerial refueling crews scored 198 out of 200 points, taking on 40,000 pounds in less than 8 minutes each time. The value of this refueling capability with existing tankers is obvious. It means that the Hustler has intercontinental range and can hit SAC targets around the world from bases in the United States. Indeed, the B-58's performance served as an overall demonstration under combat conditions of SAC's current mission capabilities. Although they did not participate in the games, Royal Air Force crews were present as official observers, emphasizing that the B-58 is the free world's only operational supersonic bomber. January 12, 1961, Edwards Air Force Base, California. One SAC B-58 bomber carrying a 4,000-pound payload set 6 new world speed records in a single flight. 5 of these records were owned by the Soviet Union. The National Aeronautic Association oversaw the record-breaking flight and sent certification data to the Fédération Aéronautique Internationale in Paris, France. NAA observers were stationed at each turning point, where official sighting stations were put up to ensure that the bomber, which had a maximum ground speed of 1,425 miles per hour, did not cut inside the pylons on turns shortening the needed course distance. This run aimed to break the 2,000-kilometer record. 2 loops around the track with a weight of 2,000 kilograms, approximately 4,000 pounds. The B-58's three-person crew was as follows: Major Henry Dutchendorf, pilot; Captain William Palamas, navigator bombardier; and Captain Wagoner, defensive system operator. All officers from the 65th Squadron of the 43rd, the Air Force's 1st B-58 Bomber Wing at Carswell Air Force Base in Fort Worth, Texas. Major General Niels Oman, commander of the 19th Air Division of the 2nd Air Force, and Colonel James Johnson, the crew's commanding officer, were on standby to watch the flight path. Chase planes carrying NOAA observers could only match the B-58's Mach 2 speed for brief periods of time. Ground observers and tracking cameras were heavily relied on for certification data. Even the tracking radar was pushed to its limits to keep up. As it crossed the starting line, N8A officials timed it and monitored its ascent to altitude. Onboard barographs, NAA officials and observation planes, as well as tracking cameras, all check altitude. The average pace was 1,061 miles per hour, setting 3 new world records for the 2,000-kilometer race and 2 loops around the 1,000-kilo track. The second lap speed of 1,200 miles per hour for 1,000 kilometers set 3 new world records. General Thomas Power of SAC's headquarters in Omaha, Nebraska, stated that the fundamental significance of these B-58 record flights is that they have significantly demonstrated the capabilities of SAC's first operational supersonic bomber. January 14, 1961, Edwards Air Force Base, California. An Air Force B-58 Hustler shattered 3 of the 6 world speed records set just 2 days before by another B-58. Major Harold Convair was the pilot, and his crew consisted of 43rd Bomb Wing officers, Major Richard Weir, navigator bombardier, and Captain Harold Biomass, defensive system operator. Today's records, like those on January 12th, were established while the airplane was climbing. Major Convair's plane started at 40,000 feet and completed at 50,000 feet. The flight required him to complete a 185-degree rotation over NAE monitored pylons, while maintaining a 60-degree bank angle and drawing more than 2 Gs, which is twice the force of gravity. From the ground, its turn appeared razor-sharp, cutting the pylon close and cleanly. The mission would have been terminated if even one cut had occurred within the crosshairs. Major Convair's crew completed the 1,000-kilometer circuit at an average speed of 1,284 miles per hour, approximately 100 miles per hour, faster than the B-58 record set 2 days before. Today is now. 2 B-58s left Edwards Air Force Base on time, following a week of record-breaking high-speed runs to return to Carswell. On the way, they flew Mach missions. Major Richard Weir, the Roadrunner's navigator bombardier, took a direct hit from a practice bombing rocket. Captain Bill Polhamus of the Untouchable submitted a score that was well within aircraft specs. Not an average or remarkable day for these B-58s, but one that will undoubtedly be memorable for its crew. Warm welcome home. Today, the news from Carswell Air Force Base is that the first wing of the world's first supersonic bomber is operational, willing, able, and ready. General Keith Compton, SAC's Deputy Director of Operations, stated this emphatically at the end of the 1960 combat competition. The outstanding bombing of the B-58 course in this competition demonstrates that the SAC now has a viable supersonic bombing competition capability. This competition has demonstrated without a doubt that this weapon system is a powerful alert vehicle with positive, accurate striking capability. Open Road 3 was a program that developed and tested a minimum interval takeoff capability for B-58 aircraft in realistic warfare scenarios. The program ran from January 14 to 22, 1963 at the Air Force Flight Test Center, and the aircraft depicted above arrived during that time. The program had 2 objectives. The primary goal was to establish a minimum safe takeoff interval between airplanes. This includes an assessment of elements such as ground turbulence in the wake of preceding aircraft jet wash, after liftoff meteorological conditions, and the impact of AB light on pilot eyesight, all during both day and night. The secondary goal was to create a method for rapidly deploying large numbers of aircraft utilizing Mach. This includes adhering to all procedures and operational standards while taxiing from a simulated alert posture under wartime scramble situations. The test program was divided into 7 test series, which comprised taxi testing in-trail takeoffs and alternate guideline takeoffs at normal and maximum growth weights. The initiative was overseen by Strategic Air Command Headquarters and carried out by the 19th Air Division. The program involved 6 B-58 aircraft and their maintenance and flight crews, 3 from Carswell Air Force Base, Texas, and 3 from Bunker Hill Air Force Base, Indiana. The first day of testing was devoted to developing taxi protocols. These studies were conducted throughout the day and again at night. These tests were used to verify scramble ground check procedures to determine how to control the space between aircraft without using excessive brakes and throttle, to determine the proper speed and radius for turning onto the runway to accelerate through the military power to afterburner range while rolling, and to determine whether airflow noise patterns and afterburner glow would affect the following aircraft. The goal was to make interval spacing completely the responsibility of the individual pilots with no outside aid. This helicopter view demonstrates the degree of regular spacing distances the pilots were able to acquire and maintain with only a small amount of practice. The taxi distance required to accomplish the ideal 15-second takeoff interval was about 300 feet. The standard spacing for lighting on taxi strips at Air Force base sites is 200 feet. Maintaining a 1.5 light distance between a leading and trailing aircraft results in an automatic 300-foot or 15-second separation. Of course, the distance would be adjusted to account for any period greater or less than this. The pilots discovered that by anticipating the use of power and brakes, they could keep the spacing distances rather consistent. This situation can be compared to the reaction required to maintain the proper flight attitude during air-to-air refueling. The projected taxi speed was calculated using the 15-second desired Mach interval to be around 15 miles per hour. Because aircraft instrumentation does not display such low speeds, an automobile was initially utilized to pace the aircraft. After a short period of time, the pilots discovered that they could assess these speeds independently. The first turns onto the runway were made at 20 miles per hour. When the turn was about 2/3 complete, the power was switched to military, and then afterburner for a takeoff simulation. After completing the first 2 runs, covering taxi to takeoff start, it was determined that this procedure caused the aircraft to deviate significantly and could potentially produce tire difficulties under maximum weight conditions. Also notice that the outboard engine's afterburner failed to light with the others, causing the aircraft to deviate slightly. This was discovered to be an extremely minor issue. Only minor steering corrections were required to return the airplane to normal while turning off the afterburner lights. The following process was devised during these trials to ensure a smooth transition from taxi to takeoff. The approach entails taxiing out with minimal power. As the aircraft approaches the runway, power is briefly advanced to military mode, and the instruments are checked to confirm that all the engines are stable. The throttle is quickly increased to full AB. This approach produced the best afterburner lights while causing no tire damage. The results of the initial taxi test revealed that there were no serious issues during this phase of operations. The second day of testing marked the start of the real flight part of the program. These tests were conducted with the aircraft operating in pairs from a standing start position. The goal here was to find the minimum safe distance between 2 airplanes taking off on the same runway. These helicopter images were captured with a slow-motion camera and do not reflect real-time intervals, which were far shorter than those seen in these high-angle panoramas. These tests were conducted with a training gross weight of 150,000 pounds. The goal here was to begin with a time interval that was well within expected safe limits, and then shorten it to investigate the effects of backwash and turbulence on the trailing aircraft. The unsticking time between the first pair of planes was 30 seconds. The second pair's time interval was lowered to 19 seconds. The unstick delay between the final two planes was lowered to 16 seconds. No difficulties were encountered. The pilots noted that these close interval single-line takeoffs were very similar to conventional individual takeoffs, with no unusual turbulence or backwash impacts observed even during liftoff and initial climb-out. Following liftoff, the aircraft used the customary alternate left and right turn pattern. All takeoffs were deemed safe. Following our single guideline test, we investigated multiple aircraft takeoffs utilizing an alternating aircraft sequence on parallel guidelines. The two lines were separated by 100 feet. As with the initial takeoff test, the aircraft were worked in pairs with time intervals steadily decreasing until a minimum safe time interval was obtained. The first two sets of takeoffs were also begun from standing start positions, with the final pair of aircraft utilizing the rolling turn Mach technique. Takeoff weights remained at the training gross weight of 150,000 pounds. The unsticking time between the first two aircraft was 13 seconds. The time between the second and third pairs was the same, 6.5 seconds. The pilots reported no serious backwash or turbulence. The harshest conditions observed were compared to what is typical of ordinary rough air takeoffs. This view depicts one of the aircraft with a minor wing down problem. At no time was more than 5 degrees of wing down seen. The largest stick displacement required to adjust for it was around 3/4 of an inch. With the B-58's capacity to conduct these takeoffs, well-established multiple aircraft takeoffs employing the rolling technique were tested. These tests were conducted both day and night and included flights with the aircraft at its maximum gross weight of 163,000 pounds. All 6 aircraft participated, and basic interval spacing was implemented at the start of the taxi runs from the ramp area. Significant throughout the experiment was the fact that conditions were identical to those found at any SAC airbase. Aircraft support was handled solely by SAC maintenance crews who arrived with the aircraft. Although the Edwards airstrip is significantly larger, the runway area employed in these experiments was limited to the standard 200-foot wide, 12,000-foot long SAC runway. The rules displayed here were painted specifically for this exercise, but they may be used at any base that requires B-58 minimum interval takeoffs. The guidelines can be added quickly and easily in a few hours. The turn pattern is created by following and painting the trail of a B-58 taxiing at 15 miles per hour. The lines can then be painted using the existing line painting equipment. The runway guidelines are 100 feet apart and parallel to the center line. They extend 1,000 feet up the runway following the turn. Unstiffed intervals for 6 aircraft with maximum gross weight takeoffs average 15.4 seconds. No severe issues were found, and all aircraft were in battle-ready condition after taking off. Pilots stated that the entire drill was extremely routine. The importance of the taxi portion of the process cannot be overstated. The key to obtaining the desired time interval is to maintain adequate spacing throughout the taxi phase of the minimal interval takeoff. Tire checks were performed during all takeoff operations, just like in a normal single aircraft. B-58 takeoffs. These were completed about 1,000 feet before reaching the runway's head with normal taxi intervals maintained. Abortion techniques are comparable to those described in the guidebook. In the event of an emergency, the pilot in the malfunctioning aircraft just says, "The conventional abort, abort, abort." Aircraft with speeds greater than the SI decision speed are unaffected. If an aircraft at a speed less than SI initiates a takeoff roll, it will immediately enter acceptable stopping procedures straight ahead. The MITO nighttime testing comprised taxi runs and demonstrations of numerous aircraft takeoffs utilizing the standard rolling technique. Both maximum training and maximum tactical growth weights were used. The ramp training weight was at 150,000 pounds. The ramp tactical growth weight was 163,000 pounds. Here, Aircraft running lights are contrasted with the runway lights as aircraft taxi from left to right. Pilots reported no ill effects in the taxi portion of the nighttime run. This film shows the engine flame as being white. This is a distinct feature of the picture. The flame from the engine afterburner looks to be a light blue-yellow tint. The program's final 2 evenings saw 2 different nocturnal sorties. There were no issues with pilot reactions to the afterburner flame from the aircraft ahead during the takeoff roll or climb out. Attempts were made to take measurements on a light meter from the plane ahead, but there was insufficient light to obtain even a minimum reading. The flight surgeon from the Air Force Flight Test Center confirmed the pilot's complaints of a lack of illumination. These night sorties demonstrated that minimum interval takeoffs of several B-58 aircraft could be performed routinely with minimal training. The training growth weight night takeoffs were performed with an average unstick interval of 11.6 seconds between aircraft. The maximum growth weight nighttime unstick intervals averaged 15.4 seconds, demonstrating complete satisfaction with all Open Road 3 program objectives. The B-58 has long proved its capacity to be operationally aware and prepared for any situation. It has also shown the ability to get wheels moving in 2 minutes and 5 seconds during simulated combat mission conditions. Any weapon system's effectiveness is defined by its ability to respond to the call and deliver a punch at the exact moment it is required. To defend a long-range missile, it is buried deep underground in a hard location. To defend an airplane, take it airborne. Today, in the case of an attack, the early warning system will give us around 15 minutes to respond. With the B-58's demonstrated capacity to scramble in large numbers employing ground alert and MITO tactics, they are confident that its odds of being caught on the ground are considerably decreased. Their demos used 6 aircraft, but the MITO capability may be configured for any number at any time from any SAC airbase. The Air Force received its first trainer version of the B-58 in August 1960. Its mission was to train Air Force pilots in the operation of the Mach 2 B-58. Since its inception, the trainer has shown to be a reliable aircraft. In its first 2 months of service, TB-58 No. 1 trained 6 pilot instructors and 7 B-58 pilots. The tale of this particular airplane began in August 1959, when the Air Force tasked Convair with producing 4 trainer aircraft. In the interest of the overall economy, it was decided to convert research and development aircraft to trainer mode, making any necessary modifications. As a first phase, a mock-up was built to demonstrate how the converted airplane will perform. Various adjustments were incorporated based on a design study. These included rearranging the second station, adding control system components, and changing the instrumentation and cockpit lighting. The new second station takes over the space that previously contained the electronic equipment for the bombing navigation system. This equipment, along with the active and passive defensive systems, has been removed from the TB-58 because they are superfluous during flights dedicated only to pilot training. The deletion of these systems resulted in significant cost savings for the trainer. In the new second station, the pilot instructor's seat is 40 inches behind the first station and 10 inches off-center. Windows have been added on either side of the ejection rail housing in the bulkhead that connects the stations. In October 1959, Research and Development Aircraft No. 11 was moved from the flight test pool to the conversion program. The Air Force accepted the aspects of redesign required in the trainer B-58, and the actual conversion of a Hustler began. With the conversion work completed, Airplane 11 was ready for ground testing. The agenda included ground run-ups for freshly installed engines, low-speed taxiing to assess ground handling characteristics, and nose-wheel steering, a high-speed taxi test, to check the dual control system brakes and drag chutes and visibility checks from the second station. After completing its ground checkout, Airplane 11 renamed TB-1. The first of 4 B-58 trainers was ready for its first flight. On May 10, 1960, B-58 trainer No. 1 took off the Carswell runway with a takeoff weight of 97,000 pounds. excluding the pod. Other conveyor shakedown flights were planned for the trainer while carrying a pod. The crew performed regular test flight activities with an emphasis on qualifying trainer-specific features, particularly the dual control system. The transfer of aircraft control from station to station was practiced. During actual training, the pilot qualifying for the B-58 will get preliminary general indoctrination while flying in the second station with the instructor at the pilot station. Following this, the in-training B-58 pilot will transfer to the front seat for the majority of his flight checkout, a method similar to that used in earlier aircraft with a tandem seat arrangement. Of course, the instructor in the second station will always have the opportunity to override the system. While these arrangements are only for training purposes, the TB has the same flying attributes as the operational B-58. For the potential B-58 pilot with no prior expertise in delta wing aircraft, considerable adjustment may be required during his first encounter with the Hustler. However, during his carefully monitored program, he will quickly realize that the stability inherent in this platform, the ease of control enhanced by its highly automated technology, and the experience of prolonged Mach 2 flying without strain have given him complete confidence in himself and his aircraft. The primary purpose of the B-58's non-tactical configuration was to instill trust, and the TB-58 now achieves this goal rapidly, affordably, and consistently. Since the commencement of aviation history at Kitty Hawk, the airman's primary objective has been to save human lives. Many methods have been utilized, ranging from the early days of the simple parachute to the complex high-altitude pressure suit of the 1950s. However, for the first time in history in 1962, the men who fly supersonic jets could save their lives without sustaining any pain or discomfort when a disabled aircraft must be abandoned. This is a chapter from Escape and Survive. In 1958, the decision was made to design and develop an enclosed seat for the ejection of an airman from the new supersonic Air Force bomber, the B-58 Hustler, built by General Dynamics, Fort Worth. Stanley Aviation Corporation of Denver, Colorado, was awarded the design and development contract. There were numerous issues that were apparent right away. Fins that extended aft from the capsule, as well as a stabilization chute, were used to regulate and stabilize the capsule following extensive research. The Hemisflow ribbon parachute was developed after numerous chutes were tested in wind tunnels and on high-speed sleds. Thus began 3 years of rigorous testing and retesting to create the new capsule. Daisy chain experiments were conducted to create harness and torso suspension solutions. Supersonic sleds are used to assess ejection characteristics. The capsule was dropped to approximate the initial landing rate of descent. Aerial drops from the Stanley T-28 to evaluate flight characteristics. After the general configuration was established, the subsystems began to take shape. The Stanley capsule was designed to give the airman the greatest amount of mobility, comfort, and utility. It has all of the necessary features to provide the absolute dependability and completeness of survival functions. During typical flights and missions, it functions as an adjustable seat. Given that most pilots will never employ the escape system for its intended purpose of escape and survival, it is irrational to burden the airman with cumbersome pressure suits. By eliminating this, the Stanley capsule exhibits shirt sleeve flying. The capsule's redundant opening and closing systems allow for fly-down while the doors are closed. This shirt sleeve concept was not just a technical feature, but a tangible benefit that pilots greatly appreciated. The flying stick is an inherent element of the capsule, and the instruments are visible through the huge plastic glass. If the situation ceases, the doors may be opened and normal flight resumed. While the subsystems were being tested, more sled runs were conducted to ensure that all systems worked properly during ejection. In addition, a high-altitude drop from a B-47 was used to test the main recovery chute. Ground rocket firings were conducted to test the escape rocket utilized in the capsule. A unique structure was built at the Stanley factory to simulate landing impact. Under controlled conditions, the capsule was dropped onto a variety of landing surfaces, including soil concrete and water. Animals were tested first, followed by human participants. One of the capsule's primary criteria is universal survival capability. Over 50 pieces of survival kit, including a 3-day supply of water and a 14-day food supply, are designed to fit into small compartments hidden within the capsule. Flotation tests were carried out under a variety of environmental circumstances, from tropical to Arctic, including a survival test on Lake Erie in the dead of winter. The person stayed in the capsule for 72 hours. During this period, he was subjected to harsh Arctic conditions, sub-zero temperatures with ice building on the capsule and violent seas. Following the test, he was inspected by medical staff and declared hale and hearty. The final test began with a static firing by a supersonic bomber parked on the runway. Following that, a series of supersonic ejections occurred from a sled on Hurricane Mesa, transporting animals. At the end of the 2-mile track, the mesa provides a recovery fall of more than 2,000 feet. The tests require meticulous preparation. The rockets have been placed and armed. A warning is delivered. The results showed that no debilitating injuries occurred during the ejections. Following that, an operable capsule was ejected from an airplane speeding down the runway at 100 knots. This test demonstrated the capsule's unique ability to eject and recover from a crippled aircraft during landing and takeoff. The first successful manned escape test above Edwards Air Force Base took place in February 1962. High-speed cameras positioned throughout the plane provide compelling evidence of the Mach 2 capabilities of the world's only functioning escape capsule. In a high-speed regime, only a capsule can give a safe escape and trust in one's survival capabilities. This confidence has been built on an unparalleled number of test injections with animals and humans. The Stanley capsule has completed all of its qualifying testing and is fully operating. As a result, another critical step in air safety has been completed, and escape and survival are now being used in practice. As the first aircraft capable of prolonged supersonic flight, the B-58 presented a unique challenge: how to safely evacuate from aircraft engaged in long-range, high-altitude military air operations. A number of requirements had to be completed to solve this problem. The most critical was to provide a safe environment for survival during ejection, descent, and landing. In this final category, both ground and sea landings had to be considered, as well as a variety of climatic circumstances ranging from tropical to frigid. Other criteria were full in-flight operational freedom for the crew at all 3 stations, as well as easy installation in tactical aircraft with minimal modification. Going beyond these standards, the Air Force and Convair collaborated to produce a basic concept of an escape system capable of greater applicability than previously imagined. This meant abandoning the design concept that required the separation of a full portion of the fuselage for escape. It also meant that the ejection system developed for the B-58 had to meet the space envelope criteria of contemporary conventional seats in any or all high-performance aircraft. A beginning point was discovered in the ejection seat a few years ago. By the space envelope idea, an interim ejection seat for the B-58 was designed to suit the normal rails while requiring no modifications to the canopy or cockpit. This system has several significant enhancements. One is the installation of extremity restraints, which will provide significantly superior protection against flailing following ejection than the present standard seat. Another option is to replace the normal catapult with a rocket catapult, which provides more force and allows for safer clearance. While the interim system is only a stage in the creation of the fully perfected escape system, it is currently the finest available. Meanwhile, under contract from Convair, the Stanley Aviation Corporation of Denver, a small but extremely capable company, was assigned the task of designing and producing an escape capsule for the tactical B-58. Despite its familiarity, the word capsule is relevant because it reflects the notion of absolute encapsulation, which is the only viable solution for crew safety at modern aircraft speeds. The detailed chronicles of the B-58 Hustler, from its meticulous ground tests to its record-shattering flights, paint a portrait of a machine built to defy limits. It was an aircraft of incredible dualities, capable of screaming across continents at twice the speed of sound, yet engineered with the unprecedented safety of a personal escape capsule. It could launch in mere minutes to answer a global threat, while also demanding a new level of precision and training from its elite crews. The B-58 was more than a weapon. It was a statement. While its time on the front lines was short, it forced a paradigm shift in strategic bombing crew safety and aerospace engineering. Its legacy is etched not only in the record books, but in the very advancement of aviation, forever remembered as the bomber that brought the future of air power into the present.